We're talking HTTP 1.0, which by default doesn't do persistent connections. So the server closes the connections after doing nothing. If I do, keep alive, the server will keep it alive for us. Or let's switch to 1.1, which requires a host header, which defaults to keep alive. Or you can ask to close, and it closes the connection for us. Let's do garbage. Oh, bad request. Server's still running. And we can look at the server logs here. We saw this is the response. The request doesn't look like much because it couldn't parse. It will print out as much as it could parse. We're using Radial as a finite state machine parser. So we parse as far as we can directly into our data structures. So we'll get, as far as there was valid data, will be logged here. We can look at the other ones, connection closed. So each one of these is running in a different fiber. So like that's a different fiber than this one. We saw the accept happen, close, the shutdown. It tried to shut down the TCP connection gracefully and then actually closed the socket. Let's do multiple. So let's put slash 1.0, content length is 5. Okay. So this request, so we accepted the connection here. Let's start another connection. Okay, so that was able to respond even though it was all in the same thread. And it's because it's the fiber engine able to handle thousands of fibers at a time, whereas this one is still waiting for the request to finish. Oh, because I can't speak HTTP sometimes. Content length is 5. Okay, that will show that we have the headers, and now we're reading the request body. Yeah. Oops, that wasn't very nice, but connection closed. Sorry, because Netcat will add the new line, which is part of the request body. I always forget that. Will be nice. So the server is also fully pipelined. As soon as one request finishes, the next request will spawn a new fiber to start processing. And then, so if one of your requests is doing something long, like sleeping, we can show a sleep, it will allow the next request to be parsed and ready. And then once it tries to write the response, that's when it will wait for its order. Is there any other questions on this? Anything else you want to see?
So what resources are required for each incoming connection? Fiber, right?
Yeah, there's
context.
There's a fiber, which has a stack. Okay. The default stack size is 1 megabyte,
wow.
But that's virtual memory.
Mm-hmm.
On POSIX systems, we use mmap to allocate the stack, which makes it so that the pages aren't actually allocated from either the page file or physical memory until they're touched. So typically, I would guess we're using less than 20 kilobytes for each one of these. And you have your socket object, you have your server connection object, and then for each request, there's a server request object. And all of that probably comes in less than a K. So if you want to handle thousands of these and you do things that sometimes use large amounts of stack, you definitely want to be running 64-bit because it does go through virtual memory. Or you can tune that down. It's just another config var. You saw me set the logging from environment variables. You can set your fiber stack size using those so that they're only 64K if you need. So On Mosey software, it's run on end user's computer, the HTTP client, and we do use a lot of pipelining. So we have to be careful that we don't do too much at once because we're running on 32-bit systems with 2 gigabytes of address space.
Okay. And is the context switch time at the fiber level comparable to a thread context switch time?
It's faster because it doesn't have to switch as much.
Like twice as fast, 10 times?
I don't have exact numbers for you, but I would guess greater than 10 times. I was talking earlier about a unit test I have that is one fiber switching between a bunch of different threads, and when it's a single CPU, you have the actual operating system thread context switches, where if it's multiple CPUs, you don't have the thread switch, it's just the fiber context switching. And on one CPU, it took upwards of a minute to run. On 2 CPUs, exact same hardware, it was a virtual machine that I just added a second CPU, the runtime went down to a couple of seconds. So it is orders of magnitude, and the reason being all it has to switch is what's necessary for the C calling convention. It just has to save a couple of registers and the stack pointer. Whereas if you're doing a OS level context switch, it has to save all of the registers, and it has to save the stack, as well as you had to be in the kernel to do that. The kernel had to do some sort of interrupt to be able to preempt the thread and do that context switch. So it is much, much faster to do a fiber context switch. Any other questions? Okay, I think we're done for this. It was great looking at both the client and the server and their similar APIs, and very easy to use. Thank you very much.